Hello everyone, this is Mr. 13 Things, kind of just coming at you with the spreadsheet proof, not a formal proof, of how a row vector, x, y, z, and then a scale, multiplied by a transformation is essentially the same thing. It becomes more or less the transpose, where you flip rows and columns, of a transformation times a column vector. But we're then going to now start talking about what in fact comprises this 4x4 transformation matrix. And again, you'll just as often see that as a 3x3 rotation scale matrix, and you might then see it as a translation vector. But this is very efficient computing. It's used by SketchUp, used by lots of others, and all it takes is for students to learn to carry around an extra 1 at the bottom of their column vector. Remember, we're going to try to get students to do dual accounting, and so to keep it separate in their brain that they're doing the same thing but they're dealing with a different audience, we're going to learn to stick our points, which probably are the ends of lines, which are the edges of faces, in column vector format. And so what I've done here, if I look here, I have laid out a matrix multiplication. If you go here, you notice when you double click on that, it shows you it's this times that. So I've done a matrix multiplication of a row vector times a transformation matrix. Hit that there. And now here, I've done the same thing, but it's a transformation matrix times a column vector. And you see, I hope, that the X, Y, and Z are color-coded, red, green, and blue, and they turn out to be the same thing. And what I'll show you, however, in a second is these essentially are the same. It is the same rotation scale matrix here, which is the identity matrix, and then the translation vector is just either stacked in this column or laid in that row with the one residing there. And what I'm going to do right now is now just apply some mumbo jumbo, if you would. I'm going to apply what would be the rotation of 45 degrees, which would be something that you do often enough. And it's going to look like this. It's going to be cosine, sine, minus sine of 45 degrees, or pi over 4, and then sine, cosine. This pattern here, cosine minus sine, sine cosine, is going to be used all the time, with one small caveat, with this negative sign flipping, depending whether or not you are doing the middle coordinate, that being the y. But you're going to see me now put those in as values, and I'm going to have to actually put pi over 4, which is about 0.78, just to, so you don't get, because the spreadsheets, again, they want to take input of radians, and so we'll talk about that as well, along with teaching your students that they're playing around with the Xbox. That you might also teach them that all of these programs, that degrees are not the be-all end-all. Military just as often uses milliradians, which are thousandths of radians, and so, and most spreadsheets take that as their default input. So what I'm going to do here is I'm going to put equal sign, open parentheses of 0.78. Bad habit, but I'm going to do it, and that's incorrect. If you notice here, I'm going to say that should be, remember, cosine 0.78. I'm going to say equals minus sine of 0.78. That's the same as 45 degrees, just so you know. Looks like I want to have, oh, it did take it, minus sine of 0.78. And when you're doing this with your students, what you may not be calling it at that point, sine and cosine, you should be calling it the y value. So we've got there, and I'm going to say this is equal sine of 0.78, and this is equals cosine of 0.78. 0.78 is not exact, but for an engineer, it's pretty close. So interesting how these numbers here should be about minus the sine of 0.78. Sine and the cosine, you'll see, are actually supposed to be equal, so that's a little bit of a computational error someplace in there. But that said, you notice how those points are translating and how this causes now a rotation and a translation. All I want to point out here is that when I go ahead and say this is equal to that, and this is equal to that, and this is equal to that, and this is equal to that, that we end up with the same transformation. And if you notice here, that does not occur. So if you notice here, this does not occur. So this is not exactly the same when it comes to how you lay these out. My presumption is this, that if I actually go ahead and transpose these two values, and so what I'm going to do is I'm going to say that equals this, and this equals that, our numbers should be the same. So what you're going to see is, and when you're dealing with this, what you're going to realize is that, once again, if you're going to be teaching students, you really want to kind of get it down to some kind of repetition. Cosine minus sine, sine, cosine. Cosine minus sine, sine, cosine. And then later on it will be cosine of 2 theta, sine of 2 theta, sine of 2 theta, cosine, minus the cosine of 2 theta for the reflection. That you really do want to tend to stick within here, and then you can do some proofs or play around so they're kind of aware of how often this mathematics just is a one thing is a flip of the other. So we notice now that these matrices look very similar, but they are in effect transposes of each other. And that may expose students into going out and looking around what a matrix transposition is, but I want to finally point out that what you want to do is get students to dual account with their points, which are the edge. The points are the ends of edges or lines, which are the edges of edges, which make up shapes, which are zombies that they're shooting back with their PSP or their DS2, and so get them to account by column vectors so they can differentiate between what their textbooks are telling you them and what the YouTube generation is doing on a regular basis on their Game Boys. Thanks for listening, and try this out.